to our new lecture, which is about lecture number 10 and 11. Okay, in this lecture, inshallah, we are going to see the three-phase induction motor principle, selection, and applications. I tried to put this lecture, these two topics in one lecture. So we are going to outline the introduction. We will see the principal components of three-phase induction motor, and we will see the principle of operation, how the rotating magnetic field work or move from move from the stator to the rotor, and we will see the direction of the rotation, how the number of poles is affecting the synchronous speed. We will see the starting characteristics of squirrel cage motor, and this is just only a summary. Okay. We will talk about motor under load. We will see the voltage and frequency induced in the rotor. Last thing is the selection, application of three-phase induction machines. We will have some examples included in the PowerPoint presentation. We will see one homework, inshallah, at the end of this lecture, inshallah. So our lecture today is about the three-phase induction motor. So we know that the induction machine or induction motors are mostly or most widely used electrical motors in industry. Inshallah, you will have the feeling, inshallah, after you finish from this lecture, and you will understand why it is mostly used. Okay, so the beautiful thing about the three-phase induction motors are is the constant speed. We will have a constant speed from no load to full load. Inshallah, you will understand it in the coming slides. Okay, now the problem with the speed control in the induction machines that the speed is dependent on the frequency. So if we need to control the speed of the induction motors, we will go through a variable frequency drive. Inshallah, this is a very advanced topic. We will not go through it, but at least you know something about it. Okay. We usually prefer DC motors when large speed variations are required. Now, the problem for induction motors, you will have a speed variation, but the range is very low. But when you use DC machines, you will have wider range of speed control. Okay, inshallah, maybe week 14 we will address, inshallah, DC motors. Okay. Now, nevertheless, the three-phase induction motors are simple. We will see. Okay. Rigid, low-priced, easy to maintain, and can be manufactured with characteristics to suit most industrial requirements. Okay. So in this chapter, we shall focus our attention on the general principle of three-phase induction motor. We will see the main parts of induction motors. And we know that the main parts of induction motors are stator and rotor. Stator and rotor. The principle of the induction motors are simply when you apply three-phase voltage to the winding of the stator winding, you will have a three-phase rotating magnetic field. Okay. In the rotor, you will find either you have aluminium bars for squirrel cage induction motors, or windings for the rotor, which is for one rotor induction motor. Sorry for the background sound. I apologize. Now, for the rotor winding derives its voltage and power from the external energized stator winding through electromagnetic induction. So by the name, okay, of this motor, which is induction, we know that the voltage or the magnetic field is going from the stator to the rotor by electromagnetic induction. By electromagnetic induction. Okay, let's go back to the principle of transformer, and we will understand the real principle of operation. So let's say we have a transformer, right? This is the core of the transformer. Okay, we will have a primary winding here, and we will have secondary winding. Okay, so this is the primary winding, and once we apply voltage here, let's say 120 volts. Okay, now when we apply voltage, and of course this voltage is going to if because with the circuit here is closed, we will have current, and this current is going to, if we have as Faraday's law said, if we have a coil and a current going through it, we will have a magnetic field induced in this coil. Okay, magnetic field induced in this coil. So we will have a magnetic field, and this core is going to be magnetized, right? And this magnetic field will go from this side to the other side, which is the secondary part of the transformer. As we know that we will have a magnetic field, okay, and this is the coil. We will have a voltage induced because of the magnetic field, and if we have a load here, right, we will have a current going through the coil. Okay, this is the principle of transformers. Okay, now the difference is like this. Let us see together. So in case of induction motors, we will have a stator as we explained, and this is the fixed part of the machine. Okay, this is the fixed part of the machine. Okay, when we apply three-phase voltage, right, three-phase on the coil, we understand that we have a rotor here, and this rotor will be rotate because we have short circuit either coil or aluminum bars, and we will have a magnetic field going from the stator winding to the rotor winding through electromagnetic induction principle. Okay, because we have an air gap, right? In order to move the rotor, we will have an air gap between the stator and rotor. Okay, so the electromagnetic field will go from the stator to the rotor through the air gap, and this is called induction. This is called induction, and this is just only the principle. The air gap is usually between 0.4 millimeter to 4 millimeter, which is very small space. Okay, if we have let's say we have 1 centimeter air gap, then we will not we are not going to have the magnetic field going from the stator to the rotor because of the space, because it is very large space. Please understand that 0.4 millimeter is nothing, is very small area. Okay, a very small space for the magnetic field to go from the stator to the rotor. Okay, now let's go deep about the stator. The stator, as we know, this is the fixed part of the motor, and here we will have the winding of the motor, three-phase winding. Okay, this is the three-phase winding. Of course, the three-phase windings are separated by 120 degree, as we know that in three-phase system we will have one phase is starting from 0, and the other phase is starting from 120 degree, and the other is starting here from 120 degree from the second wave. So we will have a three-phase voltage, and we will have three-phase magnetic field in the stator. Okay, so it consists of a steel frame. This is the steel frame, right? This is the steel frame. Encloses a hollow. This is hollow because we have empty space here, right? Hollow means empty space. Cylindrical core made up of thin lamination of silicon steel. So this core, right, is consists of thin. You will see it in the video, inshallah. We will show you a video, inshallah. So we will have a laminated steel, um, uh, lamination of silicon steel to reduce the hysteresis and eddy current. We know that to the eddy current, I think I explained the eddy current before. Let me just give you just only the what is the effect of the eddy current. Okay, so this is the transformer. Again, this is the iron core. Okay, the iron core is not only like this. Okay, so the current, if we have a magnetic core like this, so it is not laminated sheets, we will have thick metal, then the current will go like this. So it will, the direction of the current will be not organized, and this will cause a heat. Will cause a heat in the transformer, and this is a big issue because we will have losses. Sorry, and this is a big issue in the transformer. That's why we make the iron core of the transformer laminated sheets. Okay, it is like sheet together and laminated from each other to force the current to move in one direction. Okay, so if the current moves in one direction, then we will have no problem. We will not cause heat in the core of the transformer, and the losses will be reduced. Okay, it is the same principle for the stator. Okay, a number of evenly spaced slots are provided on the inner. This is the slots. Okay, it's evenly distributed. The insulated connected to form a balanced three-phase star or delta connected circuit. So we will have a three-phase winding, right? We'll have sorry. If you apply three-phase voltage here, we will have, of course, inside three windings separated by 120 degree, and the end of the windings. Okay, the end of the windings are either connected as a star, which is mostly used, or delta. Sorry for that. So this is these are the stator windings, and the three-phase stator winding is wound for a definite number of poles. Okay, greater the number of poles, lesser the speed of the motor. This is very important note here, okay? This is very important note. So we will have more poles in the stator, we will have less speed or less synchronous speed, okay? When three-phase supply is given to the stator winding, a rotating magnetic field of a constant magnitude is produced. Okay, so when you apply three-phase voltage, okay, we will have a rotating magnetic field in the stator as Faraday's law. So this rotating magnetic field induces current in the rotor by electromagnetic induction. Now, this is the rotor of the induction motor. We have two types of rotors. One of them is called squirrel cage type, and the other is wound type. So the rotor mounted on the shaft is a hollow laminated core again. So it is laminated core again, and we will see in the video, having slots on its outer periphery. The winding placed in these slots called rotor windings may be one of the following two types. Okay, the squirrel cage motor right now, the squirrel cage rotor, it consists of laminated cylindrical core. This is core laminated. This is one, this is two, this is three. So it is cut like this, and it is laminated, and then we will have cover bars like this, okay, to connect between them, and end rings to short the aluminum bars, then to have a path for the current if we have the magnetic field from the stator. Okay. For the squirrel cage, as you can see here, the rotor, this is the real picture of squirrel cage rotor. As you can see, this is the aluminum bars, and these are this is the ring, and from other side again, and this is core, which is a laminated core like this. So we have sheets, okay, sheets together, and then we will have it is laminated from each other to remove the eddy current, okay, as we explained. Okay, most of three-phase induction motors use a squirrel cage rotor as it is as it has a remarkably simple construction, enabling to operate in most adverse circumstances. Okay, however, now the problem of the squirrel cage induction motors, it suffers from disadvantage of low starting current. This is a very serious problem with the squirrel cage induction motor because it is because the rotor bars are permanently short circuited, and it is not possible to add any external resistance to the rotor circuit to have a large starting current. So if we have a resistance, if we can insert the resistance in the squirrel cage, then we will have high starting torque. But the problem that we have only aluminum bars and it is short circuited. We don't have a winding, and this is in case of huge loads, we need starting current, starting torque, right? Then this type of squirrel cage rotor is not helping me in this matter, so I will use wound rotor. Okay, wound rotor. Now, the wound rotor is again same as the squirrel cage, but we have a winding. As you can see here, this is the winding. This is the winding. Okay. So this is the rotor winding. So we have three windings. Okay, connected to the slip ring, and from the brushes, as you can see here, the brushes we can take. We can connect it to the rheostat. So this is the slip ring, okay, and we will have brushes here. Brushes are made of carbon, okay, to take out the current from the slip ring. So we will have friction between the brushes and the slip ring, okay, and this will cause some heating problem and some losses, but still we can have high starting current. Okay, so please read this paragraph. The importance of this slide is the external resistance are used during starting period only. When the motor attains normal speed, the three brushes are short-circuited so that the wound rotor runs like a squirrel cage. Okay. Now, this is very beautiful photo for the induction motor. Okay, and this is actually squirrel cage induction motor. As you can see from this picture, okay, this is the frame, right? Or we can call it yoke. Okay, yoke is written like this. Yoke is the frame of the motor that can protect the motor from any outside hazard. Okay, now these are the three-phase coil, right? Inside here, inside the slots, and we can apply the power from this terminal block. Okay. Now, this is the rotor, which is a squirrel cage type, right? Because we don't have coil here. And this is the enclosed frame for to unlock the rotor to the stator. And this is the fan to take the air from inside to outside. Okay, so that the motor will not overheat it. Okay, so these are the main parts, and this is very beautiful picture to show you everything about the squirrel cage induction motor. Now, as you can see here, we have a three phase, which is phase A, phase B, and phase C. As you can see, phase C here is having a winding from this side to this side, right? It is connected in such a way that it will not interact with the rotor. خلاص? So it is connected through the stator poles here, right? And as you can see here, the winding of A, and here is the winding of B, and here is the winding for C. So we have three phase windings separated by 120 degree, and the current flowing from the line to the neutral are considered to be positive. Now, just erase this one. Now, the rotating field, when we connect the primary winding or the stator to a three-phase AC source, it establishes rotating magnetic field. Okay, now, this rotating magnetic field rotates at synchronous speed. We will understand the synchronous speed in the coming slides, okay? But make sure that you understand that the synchronous speed, if you have the same number of poles as the generator from Skiko, we will have the same synchronous speed. Okay, so we will have the rotating magnetic field from the supply, right? From the Skiko company. Now, according to Faraday's law, an EMF induced in any circuit is due to rate of change of magnetic flux linkage through the circuit. And this is we explained before. As the rotor winding, the winding in an induction motor are either closed through an external resistance or direct shorted by end rings, either squirrel cage or wound rotor, and cut the stator rotating magnetic field. An EMF is induced in the rotor cover part, and due to this EMF, electromotive force, a current flows in the rotor winding. So we will have a rotor here, right? This is the rotor, right? This is this is the end of the stator right here, and we will have the rotor here inside. Okay, and as you know, this is the air gap. This is the air gap. The rotor will not touch the stator, right? We will have small air gap in order to move the rotor. So if we have a rotating magnetic field here, the stator, either clockwise or anti-clockwise, then we will have this rotating magnetic field will go to the rotor, and the rotor is short circuited, so we have closed circuit. Then we will have a rotating magnetic field or back EMF, and this will cause the magnetic field to interact to the rotor bars, and then we will have a magnetic field in the rotor to interact with the stator. Then we will have a movement. Okay. So here the relative speed between the rotating flux and the stator static rotor conductor is the cause of the current generation. Hence, as per Lenz's law, the rotor will rotate in the same direction to reduce the relative velocity. So we will have a rotating magnetic field from the stator, and this magnetic field will go to the rotor by induction. And this magnetic field, because we have a closed circuit, then we will have a current, and this current will produce back EMF. This EMF is going to have a magnetic field, and this magnetic field, the static magnetic field, will interact with the stator winding magnetic field, and then we will have a motion. Okay. Now we know that this is the three phase. From the supply. Okay. So at the beginning, as you can see here, at the beginning the rotor is 90-degree, right? And then at this point we will have, as you can see here, we have a shift angle. So we will have this is IA, right? This is IA, and it is going down, right? And this is B, and this is C. As you can see here, A is going down, and here B is going up, and C is going up. So at each time we will have two phases together. So we will have two phases together, and one phase is going down. So as you can see from this is the third part. Now IA is going down, IC is going up, and IA is going down. So we will have both. We will have two phases together, either plus or minus, to cause the rotation, right? So again here we will have two phases, which is phase A, phase C, and phase B is going down, right? So as we changing the angle of the three-phase rotating magnetic field, then the rotor is going to change. As you can see now, these are the rotation part, or the rotation magnetic field in the rotor. This will cause the rotor to move. Okay, this will cause the motor to move because we have a rotating. This is just only to show you that we have a rotating magnetic field in the stator. Now the rotating field, the working principle of three-phase induction motor, it may be observed that the rotor speed should not reach synchronous speed produced by the stator, right? If the speeds become equal, two speeds, we have stator speed, right? We have a rotor speed. So if we have the same speed here, there would be no such relative speed. We will have no speed. Okay, we will have zero speed. So no induced EMF in the rotor, and no current would be flowing. there will be no torque, and would be generated, then we will have no movement. So consequently the rotor cannot reach the synchronous speed. خلاص. We know that now the rotor of the induction machine, of the induction motor, will not reach the synchronous speed. So this difference between the stator synchronous speed and the rotor speed is called the slip. Inshallah, we will see the slip in details, inshallah, in the coming slides. Now, the rotating of the magnetic field in an induction motor has the advantage that no electrical connection needs to be made in the rotor. That means we don't have to have an electrical connection between the stator and the rotor, because the magnetic field will go from the stator, right, to the rotor by induction. No electrical connection. Okay, no electrical connection. Now, the speed of the rotating magnetic field from the stator, right, is depending on the frequency and number of poles. If we have a number of poles, let's say 4, then 120 multiply 60 divided by 4. Let's do it together. So 120 multiplied by 60 hertz, we have 7,200, and divided by 4, because we have 4 poles, then the synchronous speed is 1,800 revolution per minute. Okay, revolution per minute. Now, thus the 3-phase induction motor is self-starting. It is not like single phase. Single phase, we need a capacitor in order to start. So it is self-starting because it is 3-phase. Now, less armature reaction and brush sparking because of the absence of the commutators and brushes that may cause sparks. And this is very good for the induction motors, better than the DC machines. Okay. The construction is simple, economical, and easier to maintain. So this is, please see this video to understand the working principle of the 3-phase induction motor. This is the video. This is the link for YouTube video. It is very helpful video to understand what did I explain before. Okay, so I encourage you to see it, ya shabab. Now, as we explained, we have stator speed, right, because of the rotating magnetic field. Now we have rotor speed because we have rotor speed, because the magnetic field is transferred from the stator to the rotor. Then we have closed circuit, then we have rotor speed. Okay, now the difference between the synchronous speed and the rotor speed is called the slip. Okay, it's called the slip. Now, if it did, there would be no relative speed between the stator field and the rotor conductors, no induced. Okay, this is we explained before. Now the friction and the windage would immediately cause the rotor to slow down. Hence, the rotor speed is always less than the speed of the synchronous. This difference in speed depends upon the load on the motor. The difference between the synchronous speed and the rotating stator field is actually the rotor speed N, which is called the slip. And the quantity of N minus N is sometimes called the slip speed when the rotor is stationary. This is very important note. Okay, when the rotor is stationary, that means that the rotor is not moving. We will have in the rotor speed is 0, right? Then the slip is 1, which is 100. How is that? Because we will have N synchronous minus N rotor over N synchronous, right? Multiply 100. Now let's do it together. Now we don't have rotor speed, right? Because it is at standstill. So we will have, let's say, 800 as we derived before, minus 0 over 800, right? Multiply 100. So the slip is, so we divide by this, so it is 100%. Okay, the slip is 1. So when we have rotor speed is 0, then we'll have slip is 1. This is very important. Okay, an induction motor, the change in the slip from no load to full load is hardly 0.1% to 3%, so that it is essentially a constant speed motor. That's why it is called a constant speed motor. So if I ask you about the induction machine, and I told you that they have a constant speed motor, or they are called constant speed motors, you will say that the induction motors, the change in slip from no load to full load is between 0.1 to 3%. Okay, 0.1, this is the answer, 0.1 to 3% in the slip. That's why it is constant speed motors. خلاص. Now, this is an example or to find the slip. So a 0.5 horsepower, okay, 0.5 horsepower motor, 6-pole induction motor is excited by a 3-phase 60 hertz source. If the full load speed is 1140 revolution per minute, calculate the slip. Now we need to find the synchronous speed of this motor. The synchronous speed, as we explained, 120 multiply F divided by number of poles. So 120 multiply 60 divided by 6. So the synchronous speed of this motor is 1200 revolution per minute. Now, the difference between the synchronous speed and the revolving flux and the rotor speed is the slip speed. So ns minus n, so 1200 minus 1140 is 60 revolution per minute. So the slip is equal to ns minus n divided by ns, right? So it is 60 divided by 1200, which is 0.05 or 5%. Okay, so this is the answer. Now, the direction of rotation. So as we know that in our power supply in the lab, we have 4, 5, 6, right, terminals. This is will give me, if you connect 3 phase, right, you will give me A, B, C system. So ABC system, خلاص. And this is will give me forward or clockwise direction. So the rotor is going clockwise, and we call it forward. خلاص. Now, if we interchange between each one of them, let's say I connect not 4, 5, 6, I connect 5, 4, 6. So we will have a system which is called ACB, and then we will have a rotating magnetic field in the other direction, which is called reverse direction, which is counterclockwise or anti-clockwise. Okay, this is just only the principle of the direction of the rotation. خلاص. Now, number of poles will give me the synchronous speed, as we explained, right? So the synchronous speed is 120 multiply 60 over the number of poles. So the frequency here is always 60, right? The frequency here is always 60, and this is a constant number. So the variable here, in order to have a speed, synchronous speed, is the number of poles. So in designing the motor itself, you should identify if you need to have 800, okay, revolution per minute. So if you need 800 revolution per minute, then you have to have 4 poles. If you need to have 3600, you need to have 2 poles. So this is upon the designing and the load requirement. So to construct a 4-pole stator, the coils are distributed as shown in the figure. This is the 3. So as you can see here, we have 4 poles. This is pole number 1, and this is group number 2, which is pole number 2. This is pole number 3, and this is pole number 4, and this is the three phase system as we explained, right? So as you can see, we have an interaction between the magnetic field from the stator number from the pole number 1 to the pole number 2, as this one, right? And from pole number 2 to pole number 3, we will have an interaction. So it is like this. This is the interaction of the pole magnetic field. Okay. So we will have a connection between pole number 1 and pole number 2. We will have a connection between pole number 2 and pole number 3, and so on. Okay, that's why we have four pole uh, four pole motor. And although we have three-phase windings, but still the way connection of the poles are important in order to find the synchronous speed that you need. Okay. The winding of the other two phases are identical, but are displaced from each other from phase A by a mechanical angle of 60. Okay, so we have an electrical angle which is 120 degrees, right? This is an electrical angle, so we need to know that the angle of the three-phase windings are separated between each other, which is 120 degree. But the mechanical, we have a mechanical angle, how it is distributed, so we divide by 2. That's why we have 60, and then 60, and then 60 between each pole, and then 60. So 60, 120. Okay, this is for one winding, this is for the second winding, and we will have 60 for the third winding. Then we will have 360, which is complete circuit. Complete circle, sorry. So this is when we have the source, a revolving field having four pole connection. Four pole is created. This field rotates at only half of the speed of the second of the two pole field shown in this. Now, for the starting characteristics of a squirrel cage motor, this is a conclusion, okay? So please read it and revise it, please. So a revolving magnetic field is set up when a three-phase voltage is applied to the stator of an induction motor. We now apply the voltage to the stator windings. Now the revolving field induces a voltage in the rotor bars. Now, because the stator magnetic field will go through the rotor by induction, then we will have a voltage induced, right? So this induced voltage creates large circulating current, which flows in the rotor bars and end rings. Because we have closed circuit in the rotor, we will have a current through, right? So this current carrying rotor bars are immersed in the magnetic field created by the stator. They are therefore subjected to a strong mechanical force. Okay. Now, after we have this current carrying rotor bars, then we will have a magnetic field induced, right? So the sum of the mechanical forces on the rotor bars produces a torque which tends to drag the rotor along in the same direction as the revolving field. So this magnetic field this interaction between the two fields will cause a torque to be developed, and this torque is going to move the rotor in the direction of the stator revolving magnetic field. Okay, this is all about it. Now, if we make the motor under load, suppose that the motor is initially running at no load, means we don't have load on the shaft, right? So if we apply a mechanical load to the shaft, the motor will begin to slow down. Of course, if we apply a load on the motor, on the rotor shaft, then we will have the speed is going to be dropped down, right? Of course. So the rotor bars at high and high rate, the induced voltage and the resulting current in the bars will increase progressively because to produce greater and greater torque. Now, let me just give you this in a simple way. Now, if you apply torque to the rotor, if you apply torque, then the speed will drop, right? Speed of the rotor will drop. And now the motor is struggling to overcome this torque. Okay, right? Then it will try to draw more current, to have more voltage, to have more magnetic field, to have more torque, rotor torque, induced torque. This will try to overcome this torque from the rotor, the load, right? So it will need it needs to have more torque in order to move the load, right? The question is now, for how long can this go on؟ يعني إلى متى ممكن إن الروتر قاعد يسحب كارنت زيادة إلى متى؟ هل راح يحترق الماشين ولا وش بيصير لها؟ Okay. Now, will the speed continue to drop until the motor comes to a stop point? No. The motor and the mechanical load will reach at state of equilibrium. They will be equal when the motor torque is exactly equal to the load torque. So we have two torques here. The motor torque, which is the induced torque, and the load torque, which is on the shaft. Okay, we have induced torque, electrical induced torque from the motor, and we have mechanical torque on the shaft of the rotor. If they are equal, then we will have stability. When this stage is reached, the speed will cease to drop and the motor will return at a constant rate. So it is very important to understand that the motor only turns at a constant speed when its torque is exactly equal to the torque exerted by the mechanical load. So when they are equal, the induced torque from the motor and the torque load are equal, then we have a constant speed. خلاص. So this moment, the moment the state of equilibrium is upset, the motor speed will start to change. So إذا ما كان عندنا هذه المساواة بين induced torque والload torque, then the speed will going to change either by increasing or decreasing. If the induced voltage, now this is very important, please focus. If the induced torque of the motor is more than the torque load, then we have more speed. If we have the torque of the load is more than the induced torque of the motor, then the speed is going to be less, right? If they are equal, then we have constant speed. These are the three stages of the speed, okay, of the speed. Now, this is very important regarding the voltage and frequency induced in the rotor. The voltage and frequency induced in the rotor both depend upon the slip. Okay, they are given by the equation. So as you can see here, F2 means the rotor frequency. F means the stator frequency, which is the supply frequency. So it depends about the slip, of course, because the slip is the difference between the stator speed and the rotor speed, right? So we will have a drop in frequency. We will have a drop in frequency and we will have a drop in voltage. So that is why, as you can see here, F2 is the frequency of the voltage and the current in the rotor, and frequency of the source connected to the stator. This is the slip. So this is the difference between them. Now let us take an example. The 6-spool 1-rotor induction motor, for example, is excited by 3-phase 60 Hz source Calculate the frequency of the rotor can under the following conditions. At standstill, okay. طيب at standstill now means standstill means the rotor is zero speed. So at standstill the motor speed is zero, right? Consequently the slip is S equal to N synchronous, the speed of the synchronous, now minus the speed of the rotor divided by the speed of the synchronous, which is 1200 minus 0 divided by 1200, which is 1. As we explained before, this when the slip is 1, that means we don't have rotor speed. Now, B, motor turning at 500 revolution per minute in the same direction as the revolving field. So if now find out the frequency now. Not the frequency. Find the slip. Okay, find the slip in this condition. In this condition, the slip is 1200 minus 500 divided by 1200. Now this is the answer. This is the slip, and we can have the percentage. Now the frequency is changed for the rotor. So the frequency is slip multiply the frequency, which is 35 hertz. Okay, now for part C, motor turning at 500 and in the opposite direction of the revolving, okay. So 1200 minus 500, because it is opposite direction, divided by 1200, so it is positive. Now 1700 divided by 1200, the answer is 1.4. And as you can see, the slip greater than 1. When the slip is greater than 1, then the motor is working, or the machine is working as a generator. So a slip, Allah Akbar. A slip greater than 1 implies that the motor is operating as a brake. Okay, as a brake, and we will see why is that. The frequency of the induced voltage and the rotor current, now multiply by 60, you will have 84. So it is more than the rated frequency. So the motor speed is positive because the rotor turns in the same direction, of the field. Now this is for B. B said D. Motor turning at 2000 revolution per minute in the same direction. So we will have a minus. I gave you wrong information. So when we have a minus slip, then it means that we have a generator. If we have more than one, the slip is more than 1, then we have a brake. If we have the slip less than 1, which is positive, then that is motoring. Now, a negative slip implies that the motor is actually operating as a generator. Negative slip. The frequency now is minus 40, but in reality we don't have minus as a frequency. That's why we consider it simply as 40 hertz. Okay. Now, selection and application of three-phase induction machines. 14.1 standardization and classification of induction motors. We are about to done, inshallah. We have maybe three slides. Now, the frames of all industrial motors under 500 horsepower, okay, have standardized dimensions. Thus, a 25 horsepower, okay, motor of one manufacturer can be replaced by any manufacturer, okay, because they have the same standardized mounting holes, the same height, shaft height, and other coupling types, and this is regarding the standardization of motors of the machines or induction machines. Okay. Now, classifications according to environment and cooling method. We have five types of induction machines according to the environment and cooling method. We have drip proof motors, which is to protect the motor winding against liquid drops and solid particles. So with angle between 0 to 15 angle degrees. Sorry, the splash proof motors. It is with wider range. It is the same, but it is with wider range from 0 to 100 degree. Totally enclosed, non-ventilated motors. Totally enclosed means that the motor is enclosed with no ventilation. With no ventilation. That means it is used for wet and dusty areas to protect the motor, right? So, number four, totally enclosed fan-cooled motors, cooled by an external blast of air. So it is closed, right? But now it is cooled from a fan from outside. So it is a blast of air. So it means we blow air to the motor in order to cool it down. Now the fifth classification, which is explosion proof motors, it is used in flammable or explosive surroundings. Okay. Now, according to the line voltage changes, okay. So the most important consequences of a line voltage change is its effect upon the torque speed curve of the motor. In effect, the torque at any speed is proportional to the square of the applied voltage. Thus, if the stator, see, this is very important, okay? If the stator voltage decreases by 10%, then the torque at every speed will drop by approximately 20%. That's why we cannot change the voltage supply, because the torque will be dropped. The square of the voltage applied, so it is a very huge drop. Okay, so a line voltage drop is often produced during startup due to the heavy starting current drawn from the line. As a result of lower voltage, the starting torque may be much less than its rated value. Yes, for the single phase is basically when you have if you have three phase, as we said, we have in the lab 4, 5, 6, right? If we lose this one, we will have two phase, right? And this motor now is connected to two phase only. And if one winding, we will not have current inside, right? And we will not have a magnetic field. And this is big problem with the motor, and this may have more current in the other windings, and this will burn the remaining two windings. So the current drawn from the remaining two lines will almost double, and the motor will begin to overheat. The thermal relays protecting the motor will eventually trip the circuit breaker. خلاص عشان in order to protect the machine or the motor, then we will have protecting relays. Okay. Now, the frequency variation. The most important consequence of frequency change is the resulting change in the motor speed. So if we drop the frequency by 5%, the motor speed drops by 5%. So this is very important to know. In induction motors, the speed is dependent on the frequency. That's what we explained before, right? So if we drop frequency by 5%, then the speed will drop by 5%, which is obvious, right? Now, induction motors operating as a generator. We know that if the slip is minus, then the motor, the machine is working as a generator, right? So although induction motors turning off a three-phase line are rarely used to drive trains, now the problem that, let's say we have train, okay? This is our train, and we have straight land here, okay? Straight ground, and we will have here inclined road, okay, or let's say downward um, hill, okay, from this straight road we are going down here, right? So this train is going to go down here, right? Now, according to the gravitational force, this train is going to be speeding up, right? Now, if let's say the synchronous speed of the train is connected to synchronous or induction motor, and it works at 800 revolution per minute. Now, in this case, the motor is now increasing. It will reach like 2000. And this is more than the rated speed, right? So in this case, we will have a minus slip, right? And this will cause a generating problem. Now this machine is going to be working as a generator, and the generated voltage is going back to the source. So this is our source, this is our motor, okay? So before we apply here, we have taken three-phase voltage from here to the rotor, right? And this is rotating. The rotor is rotating here. Now the problem now, the rotor is rotating, and the power is delivered from the rotor to the source, and this is not practical, not good. Okay. Now for this selection and application of three-phase induction machines, the complete torque speed characteristics. Okay, we have seen that a three-phase squirrel cage induction motor also function as a generator or as a brake. These three modes of operation, motoring, generating, and braking, merge into each other, as can be seen from the torque speed control. Inshallah, we will see it. Next page, okay? Next slide. This curve together with the adjoining power flow diagrams illustrate that the overall properties of a three-phase squirrel cage induction machine. Okay, we see for this example, for example, that when the shaft turns in the same direction as the revolving field, okay, when the shaft turns in the same direction as the revolving field, the induction machine operates in either motor or generator. But to operate in a generator mode, the shaft must turn faster than the synchronous speed. Similarly, to operate as a motor, the shaft must turn at less than synchronous speed. Finally, in order to operate as a brake, the shaft must turn in the opposite direction to the revolving flux. This is very important in order to understand. Okay, this is the complete torque speed characteristics of an induction machine. Let me just give you, let me just zoom in. Sorry, let me zoom in. Now, as you can see, we have three modes of operation, which is brake, motoring, and generating. Okay. Now, in case of brake, we know that if we have the torque of the load is more than the torque or the induced torque of the machine, so we will have low speed. It is going to slow, and this is the brake. So this is in opposite direction, right? And this is the induced power, and this is the mechanical power. It is in opposite direction. Then we will have braking. Okay. Now, when you have induced torque here, which is the power of the rotor, and the mechanical power is in the same direction, now we will have motoring. Okay. And the third mode, which is when we have the torque of the load is more than the induced torque of the machine, or the speed of the of the rotor now is more than the synchronous speed, then we will have a generator, right? So this is the revolving speed of synchronous the synchronous speed of the revolving field, ns. uh, T is the torque developed by the machine, and N is the speed of rotation. So in case of brake, we will have an opposite torque direction, right? Then we will have this is the torque induced, and this is the mechanical torque. Now it is going to brake. Now if they are the same direction, then we will have a motoring mode. And if we have speed of the load is more than the synchronous speed, now the torque is going to be reversed. The induced torque will be reversed, and the it is going to be inducing magnetic field, and motor is going to be generator, and the generated voltage will go to the supply, okay. Now for the homework, we have 220 volt 3-phase 2-pole 50 hertz induction motor is running at a slip of 5%. Now find the speed of the magnetic field in revolution per minute. Okay, find the speed of the rotor in revolution per minute. Find the slip speed of the rotor, and find the rotor frequency in hertz. This is very easy example. Please try to find the answer. So this is the solution answer is given to you. The synchronous speed is 3000. The rotor speed is 2850, and the slip speed is 150, and the frequency of the rotor is 2.5 hertz. Please try to find. If you have any problem, we will discuss it inshallah in the coming discussion classes. Thank you so much, and I hope that you have taken the full benefit from this slide. Thank you so much.